Hi folks, welcome back. This is part 8 in the guided study stuff for the ozone story topic. Today's section turns our attention from some of the sort of general chemistry we've been looking at about haloalkanes and their reactions that make them, the radical substitution of alkanes, or reactions that involve the haloalkanes as reactants, nucleophilic substitution, or the chemistry around that, and turns our attention to the atmosphere, where this ozone story topic gets its name from, and some of the chemistry goes on there. This section will just have some sort of general ideas about the atmosphere. So first of all, let's just fill in some things you might already know a bit from school, but you need to be aware of. So if we have planet Earth, here's planet Earth. People live on Earth, and then there's trees, and there's mountains, and there's aeroplanes flying around, and all that kind of thing. All of that happens in the lowest layer of the atmosphere, and then above that is a layer that's going to be significant to the rest of this topic. So I don't know if you know this at all. Do you know what is the name of this lowest layer of the atmosphere? And that would be the troposphere or troposphere, depending on how you want to pronounce it. What about the next level up? So that is the stratosphere. And essentially life happens in the troposphere. The stratosphere is not really somewhere particularly that life as we know it goes on. Normal civil aviation doesn't fly up there. Some military jets do. You don't really get birds and things living up there. But it is important, and we'll learn more about why it's important. Okay, so that's one thing you need to know. Apart from that, you need to know basically the composition of the atmosphere, the main things present in the atmosphere. So maybe pause the video for a moment. If you had to list the gases in the atmosphere, the main gases in the atmosphere in order of abundance, and give a sort of percentage abundance for each one, what would you suggest is present? In order, you should have said nitrogen first, and then oxygen. In terms of quantity, how much, you can get very precise about this, but you are expected to have the idea that there's a lot of nitrogen, roughly 78%, and then also quite a lot of oxygen, but only about a sort of quarter of as much, so 21%. So those two together add up to sort of roughly 99% of the atmosphere. And then after that, a lot of people say carbon dioxide because it's in the news so much. But actually, no, carbon dioxide, there's tiny amounts in the atmosphere. They have very significant impact in terms of global heating. Not that that's the subject of this topic, but actually the next most abundant gas is argon, which is about 0.9%. So those are the three most abundant ones. And then carbon dioxide is actually somewhere in the territory of about 0.04% of the atmosphere. We've obviously been working on pushing that up. So if you went back in time to the beginning, to before the Industrial Revolution, you'd be talking more like 0.03%. We're now, I say 0.04 currently, it's actually probably rounds more to about 0.05. 0.05%, I think, actually, if you look at the most recent figures. Anyway, you're not supposed to know it off by heart, but it is in that sort of territory. Okay, now that leads on to a little discussion on how we convey this kind of information. The percentage is useful for nitrogen and oxygen. The numbers start to become a little bit unhelpful when you start talking about carbon dioxide. So rather than talking about percentage, you often use the measurement system of parts per million, or ppm. Note there's also parts per billion, or ppb, that gets used sometimes, but you need to know these two. And you need to be able to move between them and make sense of them. So a big part to making sense of this is that you could easily rephrase percentage as parts per 100. So, you know, for instance, if we said that 28% of the population in the UK lives in rented accommodation, I don't know. What we mean is if you divided the population of the UK into 100 equal parts, 28 of those parts would be living in rented accommodation, right? So parts per means if you think of something, a whole quantity of something in a set number of parts, how many of those parts are whatever it is you're talking about. So parts per 100, parts per million. Presumably you could have parts per 1,000 or something, but that just doesn't really get used. So how do you actually do calculations this way? So for instance, let me just give you a couple of examples. So if 2.81 grams of solid contains 0.0061 grams of, doesn't matter what, sodium ions. Calculate the sodium ion concentration as parts per million by mass. So it sounds kind of complicated, but if you can apply what you know about percentage, in percentage, you take, if you got 36 out of 50 in a test and you wanted to know your percentage, you would say that you take 36 and you divide by what the test was out of, 50, and you multiply by 100. So in this case, we're going to do exactly the same thing. We would say that we have got 0.0061 grams out of 2.81 grams. So if we were going to work that out as a percentage, you would multiply by 100. If you work it out as ppm, you simply multiply by 1,000,000. And so that comes out as, put my calculator down somewhere, 0.0061 divided by 2.81 times million, 1, 2, 3, 2, 3, 4, yeah, that's right, is 2,171. So why would we do this? Because if we worked it out as a percentage, 0.0061 divided by 2.81 times 100, it comes out as 0.217. So the reason for using one system or the other is just purely the number you get popping out of it and how convenient that is to talk about. Often people prefer to talk about numbers greater than 1 to have meaning from them. So to say something is 0.217% is perhaps not as useful a number just to talk about as to say it's 2,200-ish parts per million. And obviously, if you're not familiar with parts per million, doesn't have much meaning, but once you are, somehow it's easy to picture those kind of numbers. So there is no rule about what system you have to use unless a question tells you, you know, work this out in this way. Generally, people will go for whichever one just gives nicer numbers, I guess. And so it just depends on quantity. For things where you've got more of the stuff, you tend to use percentage. For things where you've got less of something, you tend to use parts per million in order to give convenient numbers. You can be asked to convert between the two. So converting from percentage to parts per million. So if we say that in the atmosphere, oxygen is 21% by volume, convert to ppm. We can do a similar sort of thing to what we've just done. We set up a fraction and we multiply that by 1,000,000. So the 21% is 21 hundredths. That's what that means. 21 out of the 100 parts you could divide the atmosphere into the oxygen. And so then we look at that as how many out of 1,000,000 parts, if you divided the atmosphere up into 1,000,000 parts. So 21 divided by 100 times 1,000,000 is 210,000 ppm. So this is why we use percentage with oxygen, because 21% is kind of, I don't know, easy to talk about, easy to visualize. 210,000 parts per million starts to get a bit annoying. So what about the other way, converting from ppm to percentage? Oops, didn't mean to put the title there. So let's go with the atmosphere again. In the atmosphere, CO2 equals, and let's just be a little bit more specific about this, 0.0458%. Now I'm going the wrong way. Cancel that. Let's give it another number. CO2 equals, let's go for 461 ppm. Convert to percent. So we can do exactly the same thing. You say, if I write 461 ppm as a fraction, what would that be? It would be 461 over 1,000,000. That's what 461 ppm means, that if we divide the atmosphere into 1,000,000 parts, 461 of them are CO2. So it's 461 millionths of the atmosphere. So if we want that as a percentage, we just look at what that fraction is of 100. So multiply by 100, and that should come out as 0.0461. Unless I've done something strange, just double check that. Yes, good. Percentage. So there we go. That's why we would tend to talk about it as ppm. 461 is a kind of easy number, slightly meaningful. 0.0461 doesn't just tends not to mesh with people's heads so well. Okay, if you like to memorize random things, between ppm and percentage, there is a factor of 10,000 you might have spotted. The problem with factors of conversion like that is you have to try and remember which way to do it, whether you multiply or divide. So I have to say, I would actually suggest you use this kind of logic rather than trying to apply a factor of 10,000. The reality is, if you want to turn percentage into ppm, you multiply by 10,000 because ppm number's always bigger. And if you want to go from ppm to percentage, you divide by 10,000 because the percentage number always comes out smaller than the ppm. But there we go. Okay, the other thing about the atmosphere then is that you need to know just a bit about the radiation passing through it, and have some basic, probably what you might well have from school already, sort of common sense about radiation, electromagnetic radiation. So what do you need to know? If we say here's the sun, and then over here is the Earth, this is not to scale. The gap between the Earth and the sun compared to the things the size I've drawn here is much bigger. But you should just have the idea that coming from the sun to the Earth is visible and UV radiation mostly. There's small amounts of other radiation, but that's mostly what we get from the sun. And then coming out from the Earth, there is infrared radiation and some visible, in as much as, you know, if you look at the Earth from space, it's kind of lit up because light from the sun is bouncing back out into space from it. It's not actually giving out visible light. It's not hot enough. Things only start to glow and go out visible light when they get very hot. But it's reflecting visible light. The infrared is actually given out by the Earth. The Earth warms up by when the sun shines on it and gives out infrared radiation as a result. So you just need to be aware that that's what's kind of passing through the atmosphere. Visible and UV light coming in, infrared and some visible going out. And then you should have the idea that in terms of energy, visible is in the middle out of those three. Do you know which way around the other two go? So UV and infrared. Which one is higher in energy? Which one is lower in energy? So if you're correct, you'll have said UV is higher in energy and infrared is lower in energy. The sort of beginnings of the name can help with that. Ultra, things that are ultra are kind of more, and infra is kind of less. But obviously doesn't help if those prefixes don't really mean anything to you. However, you ought to be able to also put those things on a frequency scale. So how would a frequency arrow go for these? Is it the same direction as energy, or is it a different is it the opposite direction? And you should have said that frequency and energy are proportional. So as we go up in energy, we're going up in frequency. So UV is high frequency radiation and infrared is lower frequency radiation. So what about wavelength? How does that fit with these? Is it the same relationship? Do we go up in wavelength as we go up in energy and up in frequency? Is it all the same? If you're right, you should have said no. Wavelength is the opposite. So UV is short wavelength and infrared is long wavelength, whereas UV is high frequency and infrared is lower frequency. UV is high energy and infrared is lower energy. Okay, beyond that, you ought to have just a sense of the impact that those types of radiation can cause on molecules. So the effect of radiation on molecules. Do you remember any of this from other contexts? Think about things we've done in the course so far. What about infrared? We did infrared spectroscopy not too long ago. What effect does infrared radiation have on molecules? So you should be saying that this is absorbed, exciting covalent bonds in the molecule to higher vibrational energy states. In other words, it makes covalent bonds vibrate more. What about visible then? So for this, think back to elements of life. Those atomic spectra, the atomic absorption spectrum. Visible light can be absorbed certain frequencies. What does that do? So you should say that can be absorbed by molecules exciting electrons temporarily to higher electron energy levels, they just drop back down again, right? And then finally, UV. This one we have met very, very recently. What can UV light do to a molecule? Anything spring to mind from maybe that reaction between the alkanes and the halogens? So what that should have triggered in your mind is the bond breaking idea, photodissociation, homolytic bond fission. So UV light can actually break a bond. How does it do that? Well, it's absorbed, exciting electrons to higher electron energy levels. But more so than visible light. So potentially causing bonds to break. So if you think about a bond being a shared pair of electrons, if you excite those electrons so much, they move kind of right out of the bond as they get excited, then you break the bond. So that is the photodissociation reaction. Remember, that's a type of reaction, photodissociation, light breaking a molecule. Homolytic bond fission, the type of bond breaking. That involves. And do you remember how to do the curly arrow sort of thing for this? So if you have like a bromine molecule, what did that look like? The kind of bond breaking that happens with UV light. As a clue, it produces radicals, unpaired electrons on radicals. So that's the thing where the electrons come out of the bond, not both to one end, but each end gets one electron. So they both have the same outcome. They both end up with an unpaired electron. So the homolytic bond fission. So we get the two bromine radicals. Okay, that will do for this little video.